It's funny. We take something as simple as walking for granted. But have you ever stopped to think about the incredible physics at play every time you take a step?
Hmm.
It's Newton's laws in action. And today, we're going on a deep dive to unpack these fundamental principles. We'll be using this quirky little book called The Case of the Walking Dog.
Oh, it's amazing how much we can learn about the universe by observing something as seemingly mundane as a dog stroll. This
Right.
book uses that everyday scenario to break down complex ideas from Newton's Principia. It makes them surprisingly relatable and easy to understand.
This deep dive is for anyone who's ever felt intimidated by physics, or even just curious about the forces that shape our world. We'll uncover the hidden depths of Newton's laws and see how they apply to everything, from a dog walking to the motion of planets.
And what's really fascinating about this book is that it doesn't just present the laws as cold, hard facts. It uses a dialogue format and even cartoons to explore the why behind them. It encourages you to question your assumptions and think critically about how things work.
Okay, let's start with the laws themselves. You've probably heard them before. An object at rest stays at rest, EFMA, and for every action there's an equal and opposite reaction. Seems simple enough, right?
Well, the book immediately challenges that perception. It points out that even a dog at rest isn't truly at rest.
Oh.
At a microscopic level, there's constant motion. Cells dividing, blood flowing, and even atoms vibrating. And on a larger scale, the Earth itself is rotating and orbiting the sun. So even stillness is relative.
That's a great example of how this book makes you stop and think.
Yeah.
We often take these laws at face value, but there's a lot more to them than meets the eye.
Exactly. And this idea of questioning assumptions, that is key to understanding Newton's work. It's not just about memorizing formulas, it's about developing a deeper understanding of the principles behind them.
The book also tackles some common misconceptions about the laws, especially the third law, the one about action and reaction. Uses a rather vivid example of a student getting slapped.
Now, before you think this book condones violence, the slap is just a memorable way to illustrate a point.
Okay.
The idea is to highlight that the forces in an action-reaction pair act on different objects. The hand-slapping experiences a force, and the face being slapped experiences an equal and opposite force.
Right. It's easy to misinterpret this law and think that the forces should cancel each other out. But the book makes it clear that these forces act on separate entities, leading to different outcomes.
Precisely. The book emphasizes that understanding this concept is crucial for analyzing a wide range of interactions, from collisions to the seemingly simple act of standing on the ground.
Speaking of forces, let's talk about tug of war. It's a classic example of how the third law can seem counterintuitive. If the forces are equal and opposite, how can one side win?
That's where the book introduces the concept of Newton's half-law. It's the idea that each particle acts independently of other particles.
Okay.
It's not about the overall force exerted by each team, but rather the individual forces between the rope, the people, and the ground.
So the winner of a tug of war isn't necessarily the team pulling harder on the rope, but the one with a better grip on the ground.
Exactly. They're able to exert a greater force against the Earth, and that's what ultimately determines victory. It's a fascinating example of how a deeper understanding of Newton's laws can reveal the subtle physics at play, even in everyday activities.
The book also uses cartoons to explain some of the more abstract concepts,
Yeah.
like the idea of idealized objects. I especially love the one with the elephant trying to wrap its head around it.
That's a perfect example of how the book uses humor to make complex ideas more digestible. The elephant cartoon highlights how Newton simplified real-world objects to make his calculations and models more manageable. He might treat a planet as a single point in space, even though we know it's a massive, complex sphere.
So it's like creating a mental model, right? Focusing on the key elements, ignoring the less important details to understand the big picture. It's something we all do in our daily lives, not just in physics.
Absolutely, and recognizing that Newton's laws rely on this type of simplification helps us appreciate their elegance and power.
Now, one of the most engaging parts of the book is the dialogue between Galileo and Aristotle. It's like a mini play within the book that brings to life the historical debates surrounding Newton's first law.
For centuries, Aristotle's view of motion reigned supreme. He believed that objects naturally come to rest, and that any motion required a continuous force. This made sense based on our everyday experience. A ball rolling on the ground eventually stops.
Right.
But Galileo, through his experiments, challenged this long-held belief, didn't he?
He did.
He used simple, elegant experiments like sliding a duster across a table to demonstrate that objects in motion tend to stay in motion.
Yeah.
He argued that it's actually external forces like friction that cause them to slow down and eventually stop. This was a revolutionary idea that paved the way for Newton's first law.
So it was a complete shift in thinking, from seeing rest as a natural state to recognizing motion as equally natural. And what's really cool is how the book uses this historical context to highlight the importance of questioning assumptions and relying on observation and experimentation.
It's a fantastic illustration of how scientific progress often involves challenging established ideas. And building upon the work of those who came before us, it reminds us that our understanding of the universe is constantly evolving as we make new discoveries and refine our models.
And this leads us to one of the most awe-inspiring applications of Newton's laws: planetary motion. What is it that keeps these massive celestial objects in orbit? Why don't they just fly off in a straight line?
That's the question that consumed Newton. And his answer revolutionized our understanding of the cosmos. He realized that the same force pulling an apple to the ground, gravity, is also responsible for keeping the moon in orbit around the Earth and the planets in orbit around the sun.
So it's all about gravity. But there must be more to it than that. I mean, gravity pulls things down, but planets are moving sideways. How do those two concepts work together to create an orbit?
To understand this, Newton used a brilliant thought experiment. He imagined firing a cannonball horizontally from the top of a very tall mountain. The faster the cannonball, the farther it travels before hitting the ground.
I'm starting to see where this is going.
Exactly. Newton realized that if you could fire the cannonball with enough velocity, it would essentially fall around the Earth.
Whoa.
It would constantly be pulled towards the center by gravity, but its forward motion would prevent it from crashing into the surface. It would be in a perpetual state of falling, which is the essence of orbital motion.
That's such a cool way to visualize it. So the cannonball is constantly falling, but the Earth is curving away beneath it at the same rate.
Precisely. And that's how planets stay in orbit. Their forward velocity is balanced by the inward pull of gravity, creating a stable, curved path.
Now, what about that famous story about the apple falling on Newton's head? Did that play a role in his understanding of gravity?
The apple story is probably more legend than fact, but it does illustrate an important point. It represents Newton's realization that the force of gravity wasn't limited to objects near the Earth's surface. He understood that it was a universal force, acting between any two objects with mass, no matter how far apart.
So the same force that pulls the apple down is also pulling the moon towards the Earth, and the Earth towards the sun.
Exactly. And the strength of this force depends on the masses of the objects and the distance between them. The more massive the objects and the closer they are, the stronger the gravitational pull.
That makes sense. But how did Newton actually prove this? He couldn't exactly measure the gravitational force between the Earth and the moon.
He did it indirectly, carefully analyzing the motions of the planets and the moon. He built upon the meticulous observations of astronomers like Tycho Brahe and Johannes Kepler, who had meticulously tracked the movements of celestial bodies for years.
So he used data to support his theory, just like scientists do today.
Exactly. And while his calculations weren't perfect, he didn't have access to the precise measurements we have today. His work was groundbreaking in establishing a mathematical framework for understanding gravity and its influence on the universe.
And that framework is still used today. It's the basis for how we launch rockets, navigate spacecraft, and understand the movements of stars and galaxies.
Absolutely. Newton's law of universal gravitation is one of the cornerstones of modern physics and astronomy.
So we've covered a lot of ground here. We've talked about idealized objects, Galileo's challenge to Aristotle, and Newton's explanation of planetary motion. What's next in our deep dive into the case of the walking dog?
Well, now that we've explored the conceptual foundations of Newton's laws, the book shifts gears and dives into their practical application. It takes a step-by-step approach, starting with free body diagrams, to show how these laws can be used to analyze and solve real-world physics problems.
Free body diagrams. They sound kind of technical, but I'm intrigued. Are they like blueprints for understanding forces?
That's a great analogy. They're essentially sketches that help us visualize all the pushes and pulls acting on an object. It allows us to see the interplay of forces at a glance.
Sounds like a powerful tool. I'm eager to learn more about how they work and how we can use them to unlock the mysteries of motion.
Then let's dive right in. In the next part of our deep dive, we'll explore how the case of the walking dog uses real-world examples and clear instructions to demystify the process of applying Newton's laws. From those helpful free body diagrams to tackling complex scenarios involving friction, inclined planes, and even the feeling of weightlessness in an elevator. Stay tuned. Welcome back to our deep dive into the case of the walking dog. Before we jump into the practical applications of Newton's laws, let's take a moment to appreciate the power of simplification. Remember those idealized objects we talked about earlier?
Right, the idea of stripping away complexity, to focus on the essential elements, like treating a planet as a single point in space.
Exactly. The book gives some great examples of how Newton used this technique to make seemingly intractable problems solvable. For instance, when analyzing the motion of a ball thrown through the air, he might ignore factors like air resistance and the ball's spin, focusing solely on gravity and the initial force of the throw.
It's fascinating how reducing a problem to its core elements can reveal so much about the underlying physics. It's like clearing away the clutter to see the fundamental forces at play.
And this idea of simplification isn't just limited to physics. We use it all the time in our daily lives to make sense of complex situations, whether it's planning a trip, designing a product, or even understanding a relationship.
Right, it's about creating mental models that capture the essence of a problem without getting bogged down in unnecessary details.
Precisely. And this approach is at the heart of scientific modeling. It allows us to make predictions, test hypotheses, and gain a deeper understanding of the world around us.
Now I want to revisit that fascinating dialogue between Galileo and Aristotle. Why was their debate so pivotal in shaping our understanding of motion?
For centuries, Aristotle's view of motion was considered almost sacred. He believed that objects naturally sought rest, and that any movement required a continuous force. This made intuitive sense. If you push a cart, it stops as soon as you stop pushing.
But Galileo saw things differently, didn't he?
He did. Through a series of carefully designed experiments, he demonstrated that objects in motion tend to stay in motion. He argued that it's actually external forces, like friction, that cause objects to slow down and eventually come to rest.
And he proved this through his experiments, right? Like the one with the duster sliding across a table.
Exactly. He showed that the smoother the surface, the farther the duster would travel, indicating that it was friction, not some inherent property of the object that caused it to stop. This was a radical shift in thinking and paved the way for Newton's first law of motion.
So instead of viewing rest as the natural state, Galileo helped us see motion as equally natural. It's fascinating how this historical context enriches our understanding of these fundamental principles.
It also highlights the importance of observation and experimentation in science. It's not enough to simply accept established ideas. We must constantly test them, challenge them, and refine our understanding through empirical evidence.
Speaking of challenging established ideas, let's talk about planetary motion. How did Newton explain the seemingly impossible feat of these massive celestial objects orbiting the sun without simply flying off into space?
That was the question that drove much of Newton's work, and his answer was truly revolutionary. He realized that the same force responsible for an apple falling to the ground, gravity, was also the force keeping the moon in orbit around the Earth and the planets in orbit around the sun.
Okay, so gravity is the key, but it still seems counterintuitive. Gravity pulls things down, but planets are moving sideways. How do those two forces work together to create an orbit?
To illustrate this concept, Newton devised a brilliant thought experiment. Imagine firing a cannonball horizontally from the top of a very tall mountain. The faster the cannonball, the farther it travels before hitting the ground.
I think I see where you're going with this.
Right. Now imagine firing the cannonball with such incredible velocity that it essentially falls around the Earth. It's constantly being pulled towards the center by gravity, but its forward motion would prevent it from crashing into the surface. It's in a perpetual state of free fall, which is the essence of an orbit.
That's such a vivid way to picture it. So the cannonball is always falling, but the Earth is curving away beneath it at the same rate.
Precisely. And that's how planets stay in their orbits. Their forward velocity is perfectly balanced by the inward pull of gravity, creating a stable, curved path.
Now, what about that famous anecdote about the apple falling on Newton's head? Did that really inspire his understanding of gravity?
While the apple story is likely more folklore than historical fact, it represents a pivotal moment in Newton's thinking. It symbolizes his realization that gravity wasn't limited to objects near the Earth's surface. It was a universal force acting between any two objects with mass, regardless of distance.
So the same force pulling the apple down is also pulling the moon towards the Earth and the Earth towards the sun. It's this invisible force connecting everything in the universe.
Exactly. And the strength of this force, as Newton discovered, depends on the masses of the objects and the distance between them. The more massive the objects and the closer they are, the stronger the gravitational pull.
That makes intuitive sense. But how did Newton actually prove this? I mean, he couldn't just go out and measure the gravitational force between the Earth and the moon.
He achieved this through meticulous analysis of celestial observations. He relied on the data collected by astronomers like Tycho Brahe and Johannes Kepler, who had spent years meticulously tracking the movements of planets and the moon.
So he used data to support his theories, just like scientists do today.
Absolutely. And while Newton's calculations weren't perfectly accurate after all, he didn't have access to the sophisticated instruments and data we have today. His work was revolutionary. He provided a mathematical framework for understanding gravity that is still used today to launch rockets, navigate spacecraft, and unravel the mysteries of the cosmos.
It's amazing to think that this fundamental force governs everything from the falling of an apple to the swirling of galaxies.
It truly is. Newton's law of universal gravitation is one of the cornerstones of modern physics.
Okay, we've covered a lot of theoretical ground here. We've seen how Newton challenged established ideas, simplified complex problems, and ultimately revealed the universal force that shapes our universe. But the case of the walking dog doesn't stop there. It goes on to show us how to apply these principles to solve real-world problems.
Right, and that's where those free body diagrams come into play. Remember, they're like blueprints for understanding forces.
They help us visualize the pushes and pulls acting on an object, right?
Exactly, and the book provides a clear step-by-step approach to using these diagrams to analyze all sorts of scenarios. It starts with simple examples, like a block being pushed on a surface, and gradually builds to more complex situations.
So we start with the basics and gradually work our way up to mastering the more intricate applications of Newton's laws.
Precisely. The book breaks down the process into 3 key stages: kinematics, dynamics, and mathematics.
Kinematics is about describing motion, right? Things like position, velocity, and acceleration.
Exactly. It's like setting the scene, establishing the basic parameters of the motion we're trying to understand.
And then dynamics is where we bring in the forces, using Newton's laws to explain why things move the way they do.
Right. We analyze the forces acting on an object and how they influence its motion. And finally, mathematics allows us to calculate the precise values of these forces and make accurate predictions about the object's movement.
It sounds like a systematic approach, breaking down complex problems into manageable chunks.
It is, and the book demonstrates this process using clear examples and easy-to-follow explanations. It's like a toolbox for understanding forces in motion, equipping you with the tools and techniques to tackle a wide range of physics problems.
I'm excited to delve into these problem-solving techniques and put Newton's laws into practice. I feel like we've been building up to this, exploring the foundation before we actually start building.
That's a great way to put it. And in the next part of our deep dive, we'll explore how the case of the walking dog uses those practical tools to unlock the mysteries of motion, from the subtleties of tension in a rope to the surprising behavior of objects on inclined planes. Stay tuned.
Welcome back to our deep dive into the case of the walking dog. We've been on quite a journey with Newton's laws, haven't we? From those initial aha moments to the mind-blowing realization that the same force that pulls an apple to the ground also governs the motion of planets.
It's remarkable how these seemingly simple laws can unlock such profound insights into the workings of our universe. And what's even more impressive is how the case of the walking dog takes us beyond the theoretical. It equips us with the tools to actually apply these laws to real-world problems.
Exactly. We were just starting to explore those free body diagrams before we left off. You mentioned they're like blueprints for understanding forces. Can you elaborate on that?
Absolutely. Imagine you're trying to analyze the motion of an object, say that block being pushed across a table we discussed earlier. A free body diagram is a visual representation of all the forces acting on that block. It's a snapshot of all the pushes and pulls that are influencing its movement.
So we isolate the object we're interested in, and then represent each force with an arrow. The length of the arrow shows the strength of the force, and the direction of the arrow shows which way the force is pushing or pulling.
That's right. And by carefully considering the direction and magnitude of each force, we can start to unravel the complexities of the object's motion.
Okay, let's walk through that block example again. We have gravity pulling it down, represented by an arrow pointing straight down.
Right. And because the block isn't falling through the table, we know there must be another force acting on it. A force that's equal and opposite to gravity. That's the normal force exerted by the table on the block.
Yes, the normal force. It's the force that prevents objects from passing through each other. It's like the table is pushing back on the block, with just enough force to counter gravity.
Precisely. And we represent this normal force with an arrow pointing straight up. Now what happens when we start pushing the block horizontally to the right?
We add another force to our diagram.
Yeah.
Right? An arrow pointing to the right, representing the force of our push.
Exactly. And with this simple diagram, we can begin to analyze the block's motion using Newton's laws. We can ask, why is the block accelerating to the right?
Well, we know that an object accelerates when there's a net force acting on it. And in this case, the net force is the horizontal force we're applying.
Right, because the vertical forces, gravity, and the normal force are perfectly balanced. They cancel each other out.
So it's that unbalanced horizontal force that's causing the acceleration. And then, using Newton's second law, ESMA, we can actually calculate the exact value of that acceleration.
Precisely. We can determine how quickly the block's velocity is changing based on the force we're applying and the block's mass. It's a powerful demonstration of how these simple laws can be used to make precise predictions about the physical world.
I'm starting to see how these free body diagrams provide a clear and systematic way to approach these problems. It's like having a visual roadmap to guide our analysis.
And the beauty is that this approach can be applied to a wide range of scenarios, from the simple to the incredibly complex. The book goes on to explore situations involving friction, inclined planes, pulleys, and even circular motion.
Speaking of interesting scenarios, I was particularly intrigued by the book's discussion of tension in a rope. It's not just a simple pull, it's a force that's transmitted through the rope itself. That's a pretty subtle concept.
It is, and it often leads to confusion. Think of it this way. When you pull on a rope, the force you apply isn't just acting on the end of the rope. It's distributed throughout the entire length of the rope.
So the rope is acting as a conduit, transferring the force from your hand to whatever object the rope is attached to.
Exactly. And here's the key point. The tension in the rope is the same at every point along its length. So if you were to cut the rope in half and measure the tension at the cut ends, you'd find that it's equal on both sides.
That's pretty counterintuitive. So if I'm pulling on a rope with, say, 10 newtons of force, the tension is 10 newtons everywhere in the rope, regardless of its length.
That's right. Assuming we're talking about an idealized rope, one that's perfectly flexible and has no mass. In reality, there's always some loss of force due to friction and the weight of the rope itself. But in those idealized scenarios, the tension remains constant.
That's fascinating. It's like the force is somehow distributed evenly throughout the rope, almost magically.
It's not magic, it's physics. And it's a direct consequence of Newton's third law. Every action has an equal and opposite reaction. When you pull on the rope pulls back on you with an equal force. That force is then transmitted through the rope, creating tension.
Okay, that makes sense. And understanding this concept of tension is really important when you're analyzing systems involving pulleys, right?
Absolutely. Pulleys are essentially wheels with grooves that allow ropes to run through them. They change the direction of a force, making it easier to lift heavy objects.
The book has a whole section on pulleys, and it shows how you can use free body diagrams and Newton's laws to analyze these systems and calculate the forces involved.
It's a great example of how those fundamental principles we've been exploring can be applied to solve practical problems in engineering and everyday life.
Now, before we wrap up, I want to revisit the concept of the normal force. You mentioned earlier that it often leads to confusion, particularly when people try to identify action-reaction pairs.
Right. Remember, the normal force is the force exerted by a surface on an object in contact with it. It always acts perpendicular to the surface.
So if I'm standing on the floor is pushing up on me with a force equal to my weight. That's the normal force.
Exactly. And the common misconception is that the normal force and the object's weight are the action-reaction pair. But that's not correct.
Right. It seems intuitive at first, but then when you think about it, it doesn't quite fit the definition of action-reaction pairs.
The key is to remember that these pairs always involve forces acting on different objects. Your weight is the force of the Earth pulling down on you. The reaction to that force is the force of you pulling up on the Earth.
I remember this completely blowing my mind when we first talked about it. It still seems strange, but the more we delve into these concepts, the more it all starts to make sense.
It's a perfect example of how the case of the walking dog challenges our assumptions. and helps us develop a deeper, more nuanced understanding of Newton's laws.
It's been an incredible journey. We've gone from watching a dog walk to understanding the forces that shape the universe. I feel like I've gained a whole new appreciation for the elegance and power of Newtonian physics.
And that's the real magic of this book. It takes what can seem like intimidating concepts and makes them accessible, engaging, and even fun. It reminds us that science is not just about memorizing formulas. It's about understanding the fundamental principles that govern our world, and using those principles to solve problems, make predictions, and explore the wonders of the universe.
So what's the biggest takeaway you hope our listeners glean from this deep dive?
I hope they come away with a sense of curiosity and a desire to look at the world around them with fresh eyes. Question everything. Don't be afraid to challenge established ideas, and most importantly, never stop exploring and learning.
Well said. That's a wrap on this deep dive into Newton's laws. We hope you've enjoyed the journey as much as we have. Until next time, keep those minds curious and those questions coming.